Okay, so lecture 19. So let's just get right into it. Let's recall the setting. So recall that M is compact with boundary and we have D, which is a first order differential operator on M. We further suppose that in a neighborhood of the boundary, D is cylindrical, where A is self-adjoint, or formally adjoint, or formally self-adjoint. Okay, that's the setting that we're in, and remember we gave D APS. We defined this as the operator D B APS with respect to the A, and we considered L1, which is D APS adjoint D APS, and L2 equals D APS adjoint. Okay, so I should maybe write here that B APS of A is just the sum of the negative eigenspaces of A. Okay. All right, and then remember we also took the double of M. Okay, so we can double M. So we get an M tilde, which is the double of M. Okay, so I've included this in the lecture notes if you want to be totally rigorous about it. You know, you want to take M cross M tilde cross 0, 1, and then you identify it where this identification is x0 is identified to x1 for x in the boundary, right? So that's how you would form the double. So I mean, it is exactly what you would expect. You would have a manifold that has some boundary, and then the double would be to take another copy of it and just stick that copy like so, right? And we double by gluing along the boundary. And the point is that now we have an induced bundle E tilde, so I should say D maps from E to F, right? So E to F here. So we have E tilde, F tilde, which are the doubled bundles, and we have an induced D tilde. And the main point here is that this D tilde is smooth across the boundary because it's product. So when we double it, the coefficients remain smooth. So this is a first order elliptic. I should have said elliptic here, sorry. Okay, oops. Elliptic. Everything we do is elliptic. So this is now E tilde, F tilde, elliptic again. And now we have a closed manifold. So D tilde max is equal to D tilde min is equal to D tilde closure, and we just simply identify, so write D tilde in place of D tilde closure. So now what we did where we ended up last time was we defined another two Laplacians, so L1 tilde, which is equal to D tilde adjoint D tilde, and L2, so this is a definition, of course, is D tilde adjoint. Okay, and then I mean we know from the calculations and everything that we've done so far that the index of DAPS is what? So this is going to be now the trace of e to the minus tau d star APS D APS minus E minus tau DAPS DAPS star. So I should really also have said that it's a lemma. I mean, we're not going to prove it, but it is really so. Since so what we have is the lemma, the operators e to the minus t DAPS star DAPS and e to the minus t DAPS DAPS star are trace class for tau positive. Okay, so this is really coming out of that, right? We're not going to prove that, but that's true. So now why have we introduced these different objects here? So the point is, so let me draw the picture again, right? So let's draw the picture. So we have a cylinder here near the boundary, and then we have geometry here, right? So that's the picture that we're in. So why have we now introduced an extra Laplacian? So the point is that DAPS star and DAPS certainly identifies the index of DAPS, right? Through this trace formulation. But the point is that we want to now reduce our questions to the model operator. So the intuition here is that near the cylinder, or in the cylinder, that near the boundary, in the cylinder, the contribution to the index of DAPS should come from Laplace 1, or it should come from the trace of e to the minus t Laplace 1 minus e to the, tau, minus tau Laplace 2. Okay, so where were we? So we were back in this situation where we were just talking about the intuition of why we do this. So remember that this, where we recall e to the minus tau 1, Laplace 1 is equal to D0 APS star, D0 APS. So this is the model operator, and this is, and maybe I'll write this in the next line. And this is D0 APS, D0 APS star, right? So the point here is that in here, we should really expect contribution from the Laplace 1 and the Laplace 2. And in here, we should expect a contribution from the D tilde APS, so I wrote what this was, so L1 tilde and L2 tilde, right? So L1 and L2 really, the trace of the trace of the exponential of those operators really capture the true index in our situation, and the idea is that that near the boundary where we have no geometry, it should really come from the analysis that we've done on the cylinder, and the geometric contribution should come from this interior part. Okay, so that's the intuition here. Okay, so let me now. Okay, good. So for that reason now, so let okay. So let so for the purposes of our of this analysis, so let E1 be the kernel. So this is the so denote, maybe it's a better choice. E1, so this is the kernel, the Schwarz kernel, the heat kernel of e to the minus tau d APS APS E2 of my e to the minus, well, I can just write the Laplacians here actually. So this is L1, L2, E1 tilde is e to the minus tau L1 tilde, e tau e to the minus tau L2 tilde. Okay? Good. And so then we let K APS tau x, we let this be the trace of E1 minus E2 evaluated at the point tau xx, and K tilde tau x to be the trace of E1 tilde minus E2 tilde at tau xx. Okay? Good. And this is for, yes? No, the tilde does not denote that. The tilde is the heat kernel of the operators which are taken from first taking the double, and then we construct Laplacians out of, you know, that live on the double of the manifold, and then we take the heat kernels of that, right? Yeah. Okay. Right. Now, let's. Okay, so we are running out of Greek letters. What is a reasonable Greek letter that I can use? Now let psi 1 of t be equal to 1 in, say, 0 to rho on 2. So, okay, so we want to quantify some things, so let's assume that this cylindrical neighborhood is u rho, right? So we have to fix that. And it's 0 when we go from rho on 2 out to infinity, right? So that's such a function. So this is of course a compactly supported function on the positive reals, taking values in 0, 1, and we let psi, sorry, that's psi 1, psi 2 is just simply 1 minus psi 1. Okay. Okay, so now let's introduce some notation. Okay, so we say that f of x, or I should say f of s, g of s, sim g of s, rho on 2 to infinity.
No, the interval below.
This is 0 to 1. Is that what you mean?
Yeah.
Yeah, okay. Yes? Well, I mean, the point is that, well, it can, because it's something that's 1 here. Oops, it's a function that's okay, well,
It should be rho, not rho half.
no, I want it to be rho halves, because the point is that I want the function, so this is rho, and I want it to, so I want it to be 1, and then so it starts decaying at row half, and then it's 0 by the time it gets. Oh,
No,
you
it's
mean
strict
here?
it's
Yes.
strongly
Sorry, 3 on 4 rows. Say. Yes. You mean on the second one? Yes. Sorry. Yes. Yes, you're right. Sorry, I thought you meant the first interval. Okay. Yeah. Thanks for that. So the notation, we say Fs is similar to GS as S goes to some limit L if the limit as S goes to L of F of S divided by G of S is equal to 1. Okay? And so we say F of S is asymptotic to G of S as S goes to L, right? So this is to mean it's asymptotic. And we can ask the same in terms of an expansion. We can say that this is similar to the expansion n a n say phi n of S as S goes to some limit L if the limit as S goes to L of phi of n plus 1 S over phi of n S goes to 0, and either one of the following are true, right? And either the lim sup of S to L of f of x divided by the sum I equals 1 to n minus 1 a n phi n of, sorry, this is a S, is finite, or the limit as S to L of f of S over the sum I equals 1 to n minus 1 a n phi n of S goes to 0. Okay, so why do we want this? So we want to take some expansions of heat kernels, right? So now we can compute. So yes. Yes. Okay, so now we can compute. So now we have the following, right? So now we have, as before, let's write index of DAPS, which is equal to the trace of e to the minus tau, say L1 minus e to the tau, so trace L2. And so in this notation we've just introduced, we can actually write this now as the integral 0 to 1, integral 0 of the boundary of now the KAPS of tau T x. So why did I put x? So before, okay, so I should just say here, maybe I should have written instead of x here, I should have really written y. I should have really written y here, for the reason that now I'm inside the cylinder, right? So I'm writing these coordinates inside the cylinder now. So the y coordinate is inside the cylinder is just t and x. Okay, so that's why I'm writing it in this way. E to 1 of t d mu x dt. So that's my measure. And now I have this integral the integral now on m tilde of the k tilde of t y eta 2 of t d mu tilde of y. Okay. Good. So the eta here, the eta 2 is also just localizing into the manifold M. Okay? So we can compute this on the double, but the eta 2 is just, I mean, we've doubled, but then things are still happening inside the manifold M. So now what happens is that this expansion, this is similar to writing, this is asymptotically similar to now the k tau tx, and we can get, okay, so we can still keep the eta. So the k here, so I'll write that in the next line. So this is d mu x dt, and now this is just the integral over m, k tilde. Yes, absolutely. And I'll make a note of, so the question was, did the k lose the APS on purpose? And yes. So let me remind you what the k is. So let's just still keep this here. So, okay, so maybe I can just get rid of that now. This is just localizing, so this is just d mu y, where k tau tx is, so this is equal to the trace of what? This is equal to the trace of k1 tx tx minus k2 tau tx tx, where the ki is the heat kernel for e to the minus tau Laplace I, right? So write it on this line because it's just one. From analysis on the cylinder. Okay, so that's what we've already done before. Okay, good. Right. So now the point is that okay, so what do I want to say here? Okay, so now the point is that by the properties of this eta 1, because it becomes 0 after some period of time, we can further expand this expression and now just do the whole computations in the cylinder, right? So we can just look at tx, we can get rid of the eta, so this is d mu x dt, plus now on m we have the k tilde tau tx d mu x. Okay, so now the point now is that the heat, sorry, this is not tau x, this is y, sorry, this is y, okay. So now the point is that this heat kernel so this is now a heat kernel associated with some Laplacians on a closed manifold, so a manifold without boundary, a smooth manifold without boundary, and it's compact. So actually we have the from classical, so from the Atiyah-Singer index theorem and its heat kernel proof, we know that this actually expands as follows. Oops. So the expansion, so there's an asymptotic expansion of this from negative n for some alpha y t to the half k. Okay, right, from the heat kernel proof of the Atiyah-Singer index theorem, for d tilde elliptic and m tilde closed. Okay. Okay, so I should, all right, so what that means, so recall that we wrote kt is equal to this integral, right? So this is the integral 0 to, okay, sorry, this is 0 to infinity. This is 0 to infinity, so this is, what do you mean do we have an alpha? This is the asymptotic expansion. These are some coefficients. I mean, we have a, sorry, there's a tau, this is a tau here. So we have a heat kernel here, and the point here is that the claim is there exist alpha n, which are functions, right? For which we have such an expansion. I don't understand the question. Does that make it clear? Well, I mean, yes, when it's undefined, you can infer it from context, right? If it's an expansion of a heat kernel and you write it in this way, the alphas have to be functions, right? I mean, the k tilde is a trace, so it's a function. So if a function expands asymptotically, then these have to be functions. Okay, so recall that we had, before we wrote k tau to be this integral, right? So this was the integral of k tau x, tx d mu x dt, okay? So then what we really have is the following, right? So we have the index, so from this expression here, right? So what we have is that we have the index of DAPS is like the k tau plus the integral now over this k tilde tau y d mu y. And so what does that tell us? That tells us that this k tau is like the index of DAPS minus, now we take this expansion, right? So we take this expansion of t to a half k. Now we integrate over alpha k of x d mu of x, right? So this is what it's, so this is, of course, this is because this is only asymptotically true, right? So we're able to interchange the integrands and so on and so forth because everything that we're saying is asymptotically true. Okay, but we have an expression now, right? We have an expression that 0 to infinity of this k tau plus a half h that we wrote in this fancy way, tau to the s minus 1 d tau is equal to now the negative of the gamma function s plus a half over 2s root pi eta 2s. So from rearranging all of this, what do we get? From rearranging all of this, we end up with being able to assert that eta 2s is like negative 2s square root of pi on gamma. Actually, so let me see. That's an equal sign, actually. Aha, yes. Then we have that this is S plus a half H plus the index DAPS on S. Now we have minus the sum K equals negative N to some N over the integral alpha K X on half K plus S. So I should have said that this expansion is really for, yeah, this is a fundamental thing I didn't say. This is really as t tends to 0, right? So this is really as, tau tends to 0. This asymptotic expansion is valid as tau tends to 0. Because when we were talking about asymptotic things, we were talking about asymptotically as something tends to something. So this is d mu x now, plus some theta n of s, where these are functions, theta n of s is holomorphic for the real part of s greater than negative n plus 1 on 2. Sorry, negative here. All right. So what that allows us to do is it allows us to assert that S maps to eta of S is meromorphic. On C, and so now we get something, right? Now we get that the eta invariant, so I should have written eta A here, right there. Sorry, I should have really written eta A. So this is going to be twice this integral of just the 0th term in this heat kernel expansion, d mu x, minus h plus 2 index DAPS. Okay? All right. So what? Yes? Mm-hmm. Yes? We did this last time. This was from the analysis on the cylinder, right? So the K here is so this is integrating out the part, so this is really where we integrate the heat kernel on the cylinder. And then we differentiate, and then we get certain expressions. And then we, muck around using the fundamental theorem of calculus, and then we see that the gamma function pops out, and then the eta invariant comes out. Yes, but it's in the lecture notes, right? Yeah. Yeah. Okay. Okay. Where? I mean, there's only one eta, right? There's only one eta anywhere in this thing, and that's the eta associated with A. So yes. All right. So now let's write out the celebrated theorem of Atiyah, Patodi, and Singer. So let's really spell it out. Let M be a compact manifold with boundary. And D a differential operator of order 1 between E and F such that in a neighborhood U rho 0 rho cross M D takes the form sigma dt plus A sigma naught, where A is self-adjoint. Adapted boundary operator. Then with D equals, D APS set to be D BAPS of A, BAPS of A being the sum over the negative eigenspaces of A. Sorry, and I should, so before I just wrote this and I forgot to intersect it with H a half, right? Where this is intersected with H a half. We obtain that DAPS is elliptically regular, hence Fredholm, and the index is equal to the integral over alpha naught d mu plus, sorry, I should say minus, dim kernel of A plus this eta term divided by 2. Okay. The alpha naught is the constant term in the asymptotic expansion as tau tends to 0 of the kernel of the trace e to the minus tau d tilde star d tilde minus e to the minus tau d tilde star, where d tilde is the operator double of on M tilde, the double of the manifold. Okay. Nope. There is no assumption on any of these things. No. The Atiyah-Singer theorem is actually valid for a general elliptic first order operator. And that's really the point, right?
With explicit alpha 0.
Well, I think in the original proof of APS, they don't assume Dirac type. Right? I mean, the whole point of... I mean, of course, things become easier if you go to Dirac type, because then these heat kernel expansions, I mean, you don't even need to go to the D star D then, right? You can just look at the operator D. If you're Dirac type, then you're going to be... okay, if you're symmetric Dirac type, then basically you have something self-adjoint, right? And then the index is actually going to be 0. Okay, yeah, so then you're talking about in the even dimensional case where you have a splitting. Sure, then in that case, you can get to the to the index of the smaller operator by computing the index of the larger operator, which is 0. But the whole advantage of moving to D star D to D star tilde D tilde is precisely that this is guaranteed now to be a self-adjoint operator, even if D isn't a self-adjoint operator. And if you went into the situation of the Atiyah-Singer index theorem for Dirac type operators, and you want to just so if you look at this D plus part where you have the splitting for the spin Dirac operator, we will get onto that later on, but actually with this theorem you can apply directly to the D plus. You don't actually have to go via the splitting, right? You can just only consider the operator that now acts between the positive spinors and the negative spinors, because that is now an elliptic operator in this setting, and you can directly apply it to that. Yeah. Okay, good. So yes. No, the constant term. It's the constant term in the asymptotic expansion. So it's constant. It's the tau that's constant. I mean, for the value of tau 0, right? So this is still an integral. I mean, the alpha naught takes a value, right? So what does the asymptotic expansion look like? The asymptotic expansion is of the form, oh God. The alpha depends only on x, and it's weighted against tau. But when tau is 0, right, that's the term. So I'm talking about the constant term in terms of tau. When tau is 0, you only get the alpha. So it's the constant term for the tau, not for the variable y. Sorry, I mean the k is 0. I'm sorry, I mean the k is 0. Yes, sorry. In the expansion, the constant term is, yeah, not the tau. I want the tau to go to 0. I want this to be valid as tau tends to 0. But what I mean is the constant term in the asymptotic expansion, and that means in terms of the sum over the k. That's a good question. It's good to clarify that. So it's not constant in y. Yes, maybe say the constant coefficient. Yes, that's a good idea. So constant coefficient. Yes. Maybe I'll write that in right now. Okay, so that's the constant coefficient in the asymptotic expansion as tau tends to 0. Okay, that's good. So this is the... okay, and so... so now this defines these things where this is the double, and now what is the eta of A of S? So this is the sum over the spectrum of the non-zero eigenvalues lambda to the minus S signum of lambda, okay, which which converges absolutely for the real part of S large, and is meromorphic on all of C. Okay? Moreover, so one last remark, if the asymptotic expansion in, well, let's call it star, has no negative power, then S to eta A of S is holomorphic for the real part of S larger than negative a half. Okay, so that's the full Atiyah-Patodi-Singer index theorem. Yeah, that's the full Atiyah-Patodi-Singer index theorem. Oh, I should also say just very quickly that just here, and is finite at S equals 0, right? So, of course, we have to evaluate it at S equals 0, so we better hope that it's finite. Okay, so that's the full theorem. Okay, so let me just make a remark. So the assumption that d equals sigma naught dt plus a can be dropped. Right, so I'll tell you why we make the assumption that, well, this in a neighborhood of the boundary, I should say. Okay, so in a neighborhood of the boundary can be dropped. But then the way in which this sits in M needs to be accounted for. So this, in this situation, there is an additional contribution called the transgression form, or the transgression term. Oh, God. I'm sorry that this keeps exiting. It's because my palms are sweaty and because of the hot weather, and it certainly doesn't bode well with this tablet. It's an additional contribution called the transgression term. Depending on the second fundamental form. Okay, so I mean, this is somewhat a technicality, but I just really want to. I mean, the point of proving it in this way and making this assumption is it really clearly shows how these different terms contribute to each other, right? So let me just re-emphasize now. I mean, of course, I didn't go through the proof in detail, bashing out all of the calculations and stuff, but somehow the idea is the following, right? The idea is that in the inside part here, we have geometry. So this has geometry. And here we have somehow boundary, extended to the interior, right? That's the way to think about it. So now we want to capture the index of an operator which has a certain boundary condition for which an index theorem works. And the way that we do it is we localize into here. Oops. So we localize into here. So we use the eta. Sorry, not the eta. The psi 1. Oh, I think we called it the eta somewhere in the proof. I'll change that in the lecture notes, right? So we use this to localize, and then of course the eta 2 sees the psi 2 then sees the contribution from, say, the part here where from which it is non-zero. But somehow the amount of error in here that we get, say, from doing this analysis where maybe the eta 2 is still non-zero, that doesn't really matter. We don't really expect a cylindrical part which, you know, is which in some sense is really no geometry in the t direction at least, to make a contribution to the geometric part or the geometric contribution to the heat kernel, right? And that's the alpha naught term. And then the boundary term is of course seen by then embedding this part where we first localize by the psi 1 into the cylinder, and then that allows us to recover the expression for the eta invariant, right? So that's really the take-home message here. So if you're trying to do this kind of analysis, maybe in other situations, this is really the picture to keep in mind. Okay, so are there any questions before we move on? Okay, if not, so we've seen the Atiyah-Patodi-Singer index theorem. We've seen this term alpha naught, which we see comes from something which is an integral over something that the heat kernel sees, and I've called this a geometric term. So actually, we'll see. So now we're going to start looking more specifically at operators where this condition, particularly where we get an adapted boundary operator which is self-adjoint. So we'll start looking at situations where this assumption becomes valid, right? I mean, so far we've phrased the theorem, but we haven't really seen where it will be true. Okay, and then we'll also explicitly see as time goes on this integral over the alpha naught, how it's actually a topological term, right? It's not just a geometric term. In some situations, it's a topological term. Okay, so for that, let's talk about Dirac type operators. So I think you've already seen some of this definitions and some of these things in the exercises if you've been attending them, but let's talk about Dirac type operators, right? So for this, let's return back to a situation. I mean, here we don't need to make any assumptions about compactness or anything. So M is, Mg is now, but we assume that it's a Riemannian manifold. With boundary, right? With boundary. Okay. So now the definition. So D is Dirac type if the following symbol conditions are satisfied. So D, X, psi, adjoint, oops. paste this now. This is identity on EX, and so now I'm going to cheat and I'm going to copy and paste this. Oops, that's not what I wanted. Maybe I should have just written it out instead of trying to be fancy. Duplicate and move. Okay, now I'm going to move the adjoints, and then this has to become the identity on FX, right? So if this is satisfied, then we say that D is Dirac type. And so these are actually called, so these relations are called Clifford relations. For the symbol. Okay. So lemma. If D is Dirac type, then it is elliptic, and in fact we have that the inverse of the symbol is given as follows. So this is easily computed, right? So this is easily verified if you throw into here psi and psi, you can recover the inverse in a meaningful way. Okay. All right. There is an adjoint. Yes. There better be, because we're mapping from one bundle to the other. Okay. Sorry, yes, thank you. Thanks for noticing that. Okay. So let n now be the normal vector. So we have a metric now, so we have a normal vector, right? So now we're going to really, I mean, we had a hypothesis that we have these inward pointing vector fields throughout sort of the course and so on and so forth. But now we can start making some specific choices, right? So let n be the normal vector to the boundary along, to vector along the boundary with respect to G, and the capital N, let that be the musical isomorphism of N. Okay. So, proposition. For D in diff 1 EF Dirac type, whenever X is in the boundary, this object here, inverse, sorry, dx psi. So this is now mapping from EX back into EX, right? Because of the inverse there. Is skew Hermitian. furthermore, there exists an adapted boundary operator A that is formally self-adjoint. All right. So, what's the proof? So, can you just remind me? You haven't seen the proof of this in the exercise class, right? Okay. Well, we'll do it anyway. It's instructive. Okay. And it also helps me do some calculations which are not of a non-analytical nature. So, all right. So from what we wrote before, we have that this is the inverse is given by this following map. And of course, I should have said this should be the unit normal. I'm really sorry. I seem to be missing words. So this is the unit normal. So if it's the unit normal, then of course the inverse is the adjoint. Okay, because even when we lift up by the musical isomorphism, we maintain the unitary nature. Okay. So now, if we compose, I won't write this composition. So what do we have? So this is going to be dxn star dx psi. And from what we had from the Clifford relations, this is exactly negative dx n that's psi star dx n, and now we have an extra term, right? So we have 2g psi n I d e x. But I mean, this is also the advantage now that we have, and we are able to sort of extract out better information when we are in the situation of a normal vector. So for a normal vector, this is 0, right? So this is equal to 0 because the orthogonality also copies across to the cotangent bundle. So then we're just left with this term. And what is this? Well, this is exactly what we expect, right? So, that shows that this symbol is now skew Hermitian. Good. So, so how do we now come across an operator, an adapted boundary operator for this, which is formally self-adjoint or self-adjoint, right? So, so for the second part, just define. So let A naught be any. So we know that there are adapted boundary operators. Okay. So let A naught be an adapted boundary operator to D with the symbol of A naught xi being exactly this, right? Of course, I mean, we have to be careful. The adapted boundary operator depends on the choice of the inward pointing vector field that we choose. if we vary that, the adapted boundary operator also varies because the principal symbol condition on the operator varies, right? So it's really with respect now to this outer point in conormal, right? So that's the trick here. So now let me define. So then define A equal to a half A plus A naught, say, formal adjoint. So this is certainly now a symmetric or a formally adjoint operator, because the formal adjoint of A naught is A naught dagger, and the formal adjoint of A naught dagger is back to being A naught, right? So define this, and by construction it is formally self-adjoint. So what is now the symbol of A? Right, so the symbol now, the principal symbol of A is going to be half of the principal symbol of this plus now half of the principal symbol of the adjoint, say, or the formal adjoint, doesn't matter what we use. And this is equal to half A naught xi. And then we know from the calculations before that this is going to be minus a half of the principal symbol of the A naught. Okay, and well, what is this, right? So sorry, the A naught star, right? So this was this is from a previous lemma, right? So this is from previous lemma that we looked at very early on when we looked at the relationship between the principal symbol of the operator and its formal adjoint. But what do we have now? So by what we've just computed, because our principal symbol we've fixed to be exactly the one coming from the normal vector, induced from the normal vector, this part, as we've just computed, is just equal to plus A naught xi. So this is equal to A naught xi. Okay, so this shows that we now have an adapted operator. For Dirac type operators, we have a self-adjoint adapted operator on the boundary. Okay, so what does the Atiyah-Patodi-Singer index theorem then tell us, right? So immediately we have a corollary. Whenever D is D in diff 1EF is elliptic and Dirac type, and M is compact with G equals to dt squared plus some metric on the induced metric on the boundary near the boundary, we have okay, so what's the right way to phrase this? I'm sorry, I'm a bit lost. Sorry. So we have this near the boundary, and okay, so let me just give me 1 second for just, so we have this near the boundary, we have an A adapted operator that is self-adjoint such that d equals to sigma naught dt plus a, and the index of d, the APS with respect to this a, is precisely equal to, I'll write this a little bit more carefully in the lecture notes. D mu plus minus the index, the dimension of the kernel of this a plus the eta invariant of a now divided by 2. Okay, so all right, so yeah, let me write this a little bit more carefully in the lecture notes, but you know, the proof is basically for the appropriate a, we need to show that the metric condition g equals to dt squared plus gm implies that d equals to sigma naught dt plus a. All right. All right. Yes. Okay. So how much time do we have? So let me take a little bit more time now to maybe we can at least make a start. So we've talked about Dirac type operators, but it's interesting to also look at Dirac type operators that are formally self-adjoint, right? So that's the trajectory. I mean, we're getting increasingly more specific, right? So let's now quickly look at formally self-adjoint operators, Dirac type operators. Okay, so suppose that E is equal to F, and then that D is in diff 1 E elliptic and formally self-adjoint. Well, okay, let me make this just a part of the proposition itself. So proposition, we'll start with the proposition. Formally self-adjoint, then there exists an adapted operator A that is self-adjoint, and we have this condition here. So maybe you've seen this in the lecture notes, or in the words are just not coming to me today. In the tutorial class, unique up to the addition of a symmetric endomorphism on E, anti-commuting with the anti-commuting with the symbol. We have that this map is an isomorphism and lastly we have that the spectrum of A is symmetric and the eta invariant of S vanishes identically. Okay, so let's see now. So just a very quick question. So have you gone through the proof of this first part in the tutes? Can someone tell me that? Aha. All right. Well, okay. I guess we can just prove it. So let's begin with uniqueness. So let A1, A2 be operators, be adapted boundary operators satisfying this commutativity or anti-commutativity. Condition. So then A1 minus A2 is in diff 1E, diff 0E, right? Because they have the same principal symbol, right? So we're always using the principal symbol, which is fixing the normal, induced from the normal vector. Okay, so we're really, for Dirac type operators, at least in our discussion, we're always going to just consider the normal vector associated to the underlying metric. And so A1 is going to be equal to A2 plus A1 minus A2, right? And this is now a zeroth order term. So because it's a zeroth order term, we can see that the A1 and the A2 are unique up to the addition of exactly what we claimed, right? Okay, so for existence, let A be A naught again, be any formally self-adjoint adapted boundary operator with respect to n, or I should say capital N. Then define S equal to half of A naught plus this. Okay. Right. So what do we find? So if we take the adjoint of S, then we get that this is half A star naught plus half D N A naught star D N, right? But this is now again equal to S because we started off with the A naught being a formally self-adjoint adapted boundary operator. Okay, so now if we compute the principal symbol of this S, right? So if we compute the principal symbol, so maybe I'll leave this as an exercise in the interest of time. So S is 0 using Clifford relations. So let's just make that an exercise. So that means that S is in diff 0 of E. And then, so then set A equal to A naught minus S. So this is now equal to a half A naught minus a half D N A naught D N star. And so what happens if we compute the A star, so this is going to be A naught star minus S star, which is clearly just A naught minus S, which is again equal to A. So, okay, so we're running out of time. So again, maybe I'll just leave this calculation. So we can calculate, so exercise, so dx n a plus a, so the easiest way to calculate it is just to compute these two things separately and then add them. Right, so that gives us the commutativity or the anti-commutativity that we wanted. Okay, so that proves 1. So just bear with me for a couple of minutes because it's what we're going to do now is quite easy. So suppose now that we have this in the eigenspace of some lambda. So this means that A of d x n phi is exactly equal to, so by this anti-commutativity, it's negative of d x n tilde a phi, which is what? This is just going to be negative lambda of phi, right? So since this inverse map now is equal to negative of this, clearly this is a bijection. Okay, so the third point comes from, we know that the spectrum of A is discrete, and from 2 we have that lambda is in spec of A if and only if lambda is in spec, or negative lambda is in spec of A. So by definition, the eta is the sum over the non-zero eigenvalues of the signum of lambda s, and that's going to be 0. Okay, so all right. So next time we'll move on to more specific formally self-adjoint Dirac type operators, and I will clean up this theorem, the hypotheses, and the conclusions of this theorem a little bit more, this corollary, the application of APS in the lecture notes, because I think I have to actually work out some things here. Of course, here we're not claiming that A is unique, right? Because if I add a lower order term now, if I just add a constant number, I'm still going to have a self-adjoint adapted boundary operator, but I assume that I have that G is a product metric in the boundary, and we have an adapted boundary operator self-adjoint, so that the operator is product near the boundary, right? So I'll spell all of that stuff out in detail in the lecture notes. Okay, so thank you for the attention, and I'm sorry for these technical issues today.